Jai Hind to all. This is Dr. Shivani Agarwal. Today I am here for presenting the topic of the computer organization subject, that is the hardware implementation. So in this hardware implementation, I have to focus first for the addition subtraction algorithm, then the multiplication algorithm for the unsigned numbers, then the Booth algorithm for the signed numbers. Let's start. So this is the hardware implementation of addition subtraction. So this is for the addition and subtraction rule. In this algorithm, we have two registers, A and B register, with the sign bit AS and BS. AS for the register A, BS for the register B, and the complementer and a parallel adder. So these all the things we have to define in the hardware implementation of addition subtraction. And a very important thing that I have to use, that is the mode. That is the mode. This mode, what is the meaning of mode? Actually, this mode is the control of, first we have to do the addition or we have to do the subtraction. So if the mode value is 0, if this value is 0, that means the complementer is not working. And if the mode is 0, so it is absent in this state. So because this 0 value is go to the complementer, so the complementer is not in the working state at this time, and this input value is go to the parallel adder. So we have to add A and B register. For example, the value of register A is 0001 and the value of register B is 1000. So we have to add by using the parallel adder, and the input carry is 0. So we have to give this carry is 0 in this. With that, this perform the addition. So that shows the addition of the hardware implementation rule. Now the subtraction rule, the mode value is 1 for the subtraction. If the mode value is 1, that means the complementary is high. If the complementary is high, so we have to do that. It is A plus B complement plus 1. Complement define the complementer. So if the complementer complement the register B value as a complemented form, and if we add 1, because the input carry is 1, if we add 1 in this register, so it is perform what? A plus, it is perform actually A minus B. This is known as A plus B's complement plus 1, because we have to take the A plus 2's complement of B. So this is the basic structure of A minus B. So this is the hardware implementation of addition and subtraction. Now these are the thumb rules for the addition and subtraction. But if we have to do the operations of addition subtraction by using the sign numbers. So we have the 4 formations. If both signs are positive for both the register, both signs are negative for both the register, and one sign is positive and one sign is negative. So if the one sign is positive, one sign is negative, and we have to do the addition, so actually we have to do the subtraction. But when the both signs are positive or both signs are negative, so actually we have to do the addition. If we do the addition operation in that, if both signs are positive and we have to do the subtraction, and both signs are negative, means the signs are same, and we do the subtraction, so actually we do the addition. But if the signs are we do the subtraction. If the signs are positive and negative, both signs are changed, both signs are not same, so actually we have to do the addition. So these are the basic strategy that we have to know previously. So in this addition subtraction, we have to focus on the flow chart first. So this is the subtraction operation, this is the addition operation. So minus in A, subtrahend in B. This is A minus B, or this is A plus B. If A plus B, the augend is A and addend is B. And this is the sign bits, AS XOR BS. So what is the basic working of XOR? If both the both the bits are same, then the output is 0. If the bits are different, then the output is 1. We have to see that 0, 0, 0, 1, 1, 0, 1, 1. This is the XOR table. For the XOR operation, the output of XOR is 0, 0 is 0, 0, 1 is 1, 1, 0 is 1 and 1, 1 is 0. So, this same rule we have to apply on this addition and subtraction for the sign bit XOR. So, if both signs are same, then what happened? The output is 0. If both signs are different, then the output is 1. So, we have to already say that if the both signs are same in the subtraction, let's see, if both signs are same and we have to do the subtraction, so actually we have to do the subtraction. If the both signs are different and we have to do the subtraction, so actually we do the addition. So, we have to define this same rule in the flowchart. If both signs are same, because it is 0, AS XOR BS is 0, so we have to do the subtraction. If both signs are different, so the XOR is output is 1, that means we have to do the addition. So, this pointer show the addition rule. Just opposite in the addition, if both signs are same, then we have to do the addition. If both signs are different, then we have to perform the subtraction. So, this is the basic criteria that we have to fulfill for in defining the flowchart. Sign bits, XOR. Now, if we have to do the subtraction, so the basic subtraction rule is what? A plus B XOR plus 1, that is A minus B. So, the resultant is EA. EA means end around carry, and the overflow, this is ABF represented as the overflow. And in this case, in the subtraction rules, always the ABF is 0. There is no overflow. And because we receive the E, this is the end around carry. So, because this is a single operand value, so there are the two operations, either 0 or 1. So, if it is 0, that means this is the subtraction rule. If the output value is if the output value is not produced any carry, then we have to take the 2's complement of the resultant and put the negative sign in front of it. So, this same rule we have to use this. This is A resultant have produced A complement plus 1. This is A represents what? This shows that we have to do the complement of the resultant and add 1 in this. So, that shows what? Again the 2's complement of the resultant. So, we have to produce the value A. This is the final output in the subtraction case. So, this is the end result. But if we have to do the operation addition, so what happened with that? This is perform A plus B and the resultant is EA. In this case, the E represents as a overflow. So, we have to show that E transfers to ABF, that represent the overflow. So, actually what is the overflow condition? So, we have to proceed in the next slides. What is the overflow condition? So, we have to read the overflow conditions on that particular slides. So, if the value of E is 1, so that shows the value of A, the resultant is A. If the A value is 0, the resultant is 0, that means the sign bit is also 0. If A is not 0, so this is the resultant. So, this is the basic rule of the addition and subtraction, but this flowchart shows how we have to do the addition and subtraction by using the sign bits. So, this is the main thing that we have to define, that how we have to define the addition and subtraction by using the sign bits, if they are same or they are different. So, this rule you have to keep in your mind, that if the both signs are same and we have to do the subtraction, so actually we have to do the subtraction. But if the both signs are different and we have to do the subtraction, then actually we have to do the addition, and same thing we have to apply for the addition. If the both signs are same, that means we have to do the addition. If the both signs are different, then actually we have to do the subtraction. So, this is the addition and subtraction of the hardware implementation. Now, this is the overflow condition. So, the basic rule of the overflow condition is that The overflow condition can be detected by observing in the carry out and carry in. If both carry out and carry in XOR is 1, that means that show the overflow occurrence. If it is 0, that means there is no overflow. Let's see the example. If the plus 7 and plus 8, we have to just put these numbers into the binary. So, it is with a sign bit and in 4 bits, because the 8 bits are 1000. So, this is the highest number. So, we have to do the 7 is in 4 bits. So, it is 0111 and 1 bit for the plus sign. This is 00. So, this is the carry in, this is the carry out. So, both carry in, carry out XOR is 0 in this case. So, that means there is no overflow. But in this, the second example, if we take the carry in is 1 and carry out is 0, and we have to perform the addition, that means, and we have to do the XOR of these carry in, carry out. So, that shows, that means this is the, this XOR is high, that means there is an overflow. So, this is the overflow condition. Now, we have to move to the next topic. This is the multiplication algorithm. So, this is the very simplest rule of the multiplication without the, therefore, the unsigned numbers. So, this is what 3 multiplied by 2. So, this is what, actually this is 6, but in this form convert into the binary. So, it is 0, 1, 1, or we have to do only 1, 1, and it is 1, 0. So, this is what 0, 0 multiplied by 1, 1. So, it is 0, 1, 1. So, this resultant we have to define, it is 6. So, this is the register A, this is the register B. We have to put register A and register B, and we have to add these bits. So, we have to require the parallel adder and the complementer. If complementer required for the negative numbers, this is for the Booth algorithm. Now, this is the flow chart. In the multiplication, there are two things, multiplicand and the multiplier. So, we always say that the multiplier in B and the multiplier in Q, we have to define the numbers by B and Q as a multiplier and the multiplicand. And in initial stage, we have to say that this is the accumulator A, it is initially 0, and E, this is the end around carry, it is also 0, and the sequence counter is N. The value of sequence counter is N. So, that is completely dependent of the nth bit of Q. For example, if the Q number is this is Q. So, the nth bit of Q is this is Qn. This is the nth bit. So, this is the nth bit of Qn. So, if it is 0, if it is 0, then we have to do only the right shift. This is the logical right shift. So, in the logical right shift, we have to shift the number, and the blank space always put the 0. For example, if this is the number and we have to do the right shift, so it is 1 is out, this one is shifted here, this one is shifted here, and sorry, this 0 is shifted here, and this is the blank space, and we have to put always 0 in this. So, this is the right shift, and the sequence counter is -1. So, this is for the Qn if the Qn bit is 0. If the Qn bit is high, so what happened in this? If the Qn bit is high, so we have to perform the operation A plus B. It is transfers to EA. EA is the output. A is the resultant, E is the end around carry. So, this is the resultant, and this operation we have to perform till when the sequence counter is 0. So, after the sequence counter is 0, we have to receive the end result. So, this is the basic algorithm. Now, we have to take the example. So, we have to take the example, let me take the example of 3 and 2 that I take previously, 3 multiplied by 2. So, first we have to define the number, it is 1, 1, it is 1, 0. Multiplicand in B, multiplier in Q, multiplicand in B, multiplier in Q. And there are two, A is the accumulator, E is the end around carry. Initially, it is the value of A and E is 0. So, it is 2 because the Q register value are in 2 bits. So, we will take the 2 bits in the A, and initially 1 bit E is initially 0 and this is 1 0. Sequence counter is 2. Now what we do, first we have to find out the Qn value. The Qn value is 0. If the Qn value is 0, so what happened? We have to do the shift. We have to do the logical shift. So this 0 is out, this one is here, this 0 is here, right? And this 0 is here, this is blank, so it is again 0. And the sequence counter is -1. So this is the first step. Now the next step is what? We have to see the Qn value. It is 1. When it is 1, then we have to perform the A plus B. So A is 0 0 and B is 1 1. So we have to add that. It is 1 1, it is 0 1. We have to just copy the previous value of Q to the next value of Q, and it is initially 0, so it is 0 because there is no value occurred. Now what we happened again, we have to do the again shifting process. So this one is out, so it is 0, it is 1 1 0, again it is 0. So what happened? The resultant is this EA. The resultant is EAQ and result is EAQ. AQ is the resultant and E is the end around carry. So resultant is what? 0 1 1 0. It is 6. So the resultant is 6. So this is the multiplication algorithm. Now we have to move for the Booth algorithm. Booth algorithm we have to do for the negative numbers. So if we have the number is -3 and -2, so how we have to do the Booth algorithm? So first we have to define the flow chart. In the flow chart, initially we have to take AC is 0, Qn plus 1 is 0 and sequence counter value is n. That is dependent on the value of Q. And we have to check that Qn and Qn plus 1. There are two input values in the decision box. So actually there are the 4 combinations 0, 0, 0, 1, 1, 0 and 1, 1. If it is 0, 0, that means we have to do the arithmetic shift right. This is known as the arithmetic shift right. It is ASHR. What is the main condition of ASHR is that if we have to do the shifting like that, we have to shift that. This one is out, this one is here, this one is here, this 0 is here. So this blank space we have to fill the previous value is same copied as 0. So this is the arithmetic shift right. And we have to decrease the sequence counter value as SC goes to SC minus 1. This is same step for 0, 0 and 1, 1. But if it is 1, 0, then we have to do the AC plus BR complement plus 1. Actually, it is AC minus BR and it is AC plus BR. This is the addition, this is the subtraction. So we have to take an example for that. For example, we have to take the example of -3 multiplied by -2. And this is multiplicand, this is multiplier. And we have to say that the multiplicand in B and multiplier is Q. This is BR, this is QR. So first we have to find that this is Qn plus 1, AC, QR, Qn plus 1 and SC. This is the basic formation of the table. Now first we have to find the value of BR and QR in the binary form. So basically -3 equal to +3, it is equal to 0, 1, 1. And again then we have to take the complement of that, so it is 1, 0, 0. Then plus 1 for the 2's complement is 1, 0, 1. This is the -3 2's complement form. Then the -2. -2 means it is +2. Then it is 0, 1, 0. Then take the complement of that, it is 1, 0, 1. Add 1. If add 1, it is 1 plus 1, 0, carry 1. 1, 1. It is 1, 1, 0. So this is the BR and this is the QR. This is BR, this is QR. Okay. So we need BR complement plus 1. So again we will take the 2's complement of that. So this is the BR complement plus 1. Okay. Initially we have to take that the Qn plus 1 value is 0. So initially it is 0 and the value of QR is 1, 1, 0 and the accumulator resistor value is 0, 0, 0. Again the sequence counter is free and the Qn value is 0, so it is 0, 0. Initially we have to do the first step. If the value is 0, 0, then again we have to do the arithmetic shift right. So we do the arithmetic shift right. So it is 0 is transfer here. It is 1, 1, 0. In this 0, 0, 0. And sequence counter is -1. So it is 2. The value of Qn plus 1 is again 0 and QR, that is Qn is 0. Sorry, 1. The Qn value is 1. So if the value is 1, 0, then we have to do the AC plus BR complement plus 1. So AC BR complement plus 1, it is 0, 1, 1. We have to add this. This is 0, 1, 1. This is 1, 0. It is 0, 1, 1. It is 0. Now we have to shift. When we have to shift, so this one is shifted here. This is 1, 0, 1. This is 1, 0, 0. And sequence counter is -1. Now, the last step for this is that the Qn value is 1, Qn plus 1 is 1, 1. So we have to shift it, arithmetic shift right. So it is 1 here, it is 0, 1, 1, 0, 0, 0. And sequence counter is -1. So what happened is that it is the resultant. This is the resultant and this is the resultant of 6. So we have to do the operations like this. -3 multiplied by -2 by using the Booth algorithm. So today we have to complete this lecture with these 3 topics. Thank you.